All right, so we got a little bit slightly more complicated looking problem. We've got a piston cylinder and with water inside, and from state 1 to 2 we have a constant pressure process. So that piston head, as we cool the water in there, the piston head is allowed to move down until it hits that set of stops. And as soon as it hits that set of stops, like right at that instant, and that's at state 2, the pressure hasn't changed. It's still 1 megapascal. But then from state 2 to state 3, we continue to cool it down all the way to 70 degrees Celsius. However, because it's hit that set of stops, the volume within that piston cylinder doesn't change. It stays at 0.2 meters cubed per kilogram, or 0.2 meters cubed. And then the other thing that you'll notice is the mass does not change. So this is a sealed system. And we're also given the work for each of those processes, from state 1 to state 2 and from state 2 to state 3. And we want to find the total amount of heat transfer. So that would be the heat transfer for the first process and the second process. And then we want to get a TV diagram. So first thing we're going to do is we're going to apply the first law, and we're going to apply it for each of these processes. So let's start with the process from state 1 to state 2. So I've got Q minus W equals delta U plus delta kinetic energy and delta potential energy. And I'm going to go ahead and ignore those last two terms. Just because it doesn't look like these piston cylinders or this piston cylinder is moving around at all and changing kinetic and potential energy. So I've got delta U plus W, and those are in capital letters, and I'm going to go ahead and put those in terms of lowercase letters by bringing the mass out of the equation there, or on the outside of that equation. So the delta little u and the little w are in kilojoules per kilogram, and now I'm going to put some subscripts indicating what process I'm talking about. And I'm talking about the first process from state 1 to state 2. So now let's go ahead and figure out what U1 and U2 are. So U1 is pretty easy. I look it up in my tables and I see that I'm superheated, and I just pull that right off the superheated tables. State 2, well, I know the pressure, and I'm not explicitly given the specific volume, but I can easily calculate it. And it's just the volume divided by the mass. So I've got 0.1 meters cubed per kilogram. And if you look in your tables, you'll see that that falls within the two-phase region. So you'll be staying in those saturated tables. And you'll need to use the quality to figure out what U2 is. And the way that you're going to find the quality is by that specific volume. So you know the specific volume, it's V2. And then you could pull off the values of VF and VG and just switch around, solve for the quality at state 2. And I get a quality of 0.511571. And I'm not rounding off until the very, very end. So if I plug that in and calculate what U2 is, I got 1693.721 kilojoules per kilogram. And then if I go over and I plug everything into that Q from 1 to 2 equation, I get negative 2941.16 kilojoules. Now I'm ready to go to process 2 to 3. So there's my first law. I can go ahead and get rid of the W and the kinetic energy and potential energy changes, because I'm told that the work from state 2 to state 3 is 0. And then if I put Q in terms of m delta little u, this is the mass times the internal energy at 3 minus the internal energy at 2. And I've already figured out state 2, so that's state 2. And now I just need to figure out what I've got going on at state 3. So I know the temperature, and I also know the specific volume, because V2 and V3 are equal to one another. And I am still in the two-phase region, so I am going to have to calculate my quality, and I'm going to do that the same way that I did in state 2. So I'm going into my saturated tables that are organized by temperature, and calculating what the quality is. And if I plug in those numbers, I get a pretty low quality, 0.0196. 0.0196, and it's we usually leave off the units, but in actuality it's kilograms of saturated water vapor per kilograms of total water, so saturated water vapor plus saturated liquid water. And if I plug that into my U equation, I get 335.687 kilojoules per kilogram. So I end up calculating negative 2716.068 kilojoules for the heat transfer for the second process. And I can add those up and get negative 5657.2 kilojoules. And then you'll also see that I drew this on a TV diagram. So you'll see for the process from state 1 to state 2, the reason that it looks like this is if you recall those lines of constant pressure that we drew on a TV diagram, you could see that the process from state 1 to state 2 goes along a line of constant pressure. And then, of course, the process from 2 to 3 is a constant volume and a constant specific volume process, so it just goes straight down. And then the other thing that I actually needed to pull off, I needed to actually get two things. I needed to get the specific volume at state 1, and you can get that in the superheated tables, and it doesn't require any interpolation or anything, just pull it right off the table. And then the temperature at state 2. And you're saturated at state 2. It's just the saturation temperature at 1 megapascal. So, all right, well, I hope that was helpful. Thank you very much for watching.